Ngalakin Khadijan Nyunga Boja.
Okay, so this is video 3 in CITS1402. We're going to look at the relational model of a database. Okay, it's a very simple model at heart. Imagine if you were to build your own personal database, just listing some things that you were interested in, say, cataloging your books or your CDs or something like that. Then probably you'd just either use a plain file with a text editor, or more likely you'd use Excel. And of course there are hundreds of millions or even billions of Excel databases around, and sometimes you may even read that Excel is the world's most popular database. And to some extent that does have a grain of truth. Okay, so here's an example of the kind of thing that you might do just almost without thinking, just a very intuitive way of storing information. So I've gone through the Internet Movie Database and I've decided that I want to watch all of the highest rated movies in the next year. And so I've started by listing, by just extracting from their database the 10 highest rated movies, and I've built a spreadsheet out of that. Okay, so what are the features of this spreadsheet that are relevant to the relational data model? Well, the whole thing is a table. Okay, so it's a tabular format. It's got columns. Each column has got a name. So we have the first column is called title, and the entries in that first column are all the titles of the highest rated movies. Then there's year, and that's the year that the movie was released, director, the genre, and the IMDb rating. And you can see that the top rated movie, which is The Shawshank Redemption, has a spectacular 9.2 user rating. Okay, so this is a very intuitive tabular format. Each object, each individual movie, later we'll use the word entity to describe that. Each individual movie is one row of the table, and that row contains all of the relevant information about an individual movie. So the green row that I've highlighted is the movie Schindler's List, released 1993, directed by Steven Spielberg. Its genre. A genre is an interesting one because you see that some of these movies have just got a single genre, like drama, and this particular one has got biography, drama, and history, and we'll see that that is relevant later. Okay, so what you want to take away from this is it's a table. Each row is one object. Each column is one relevant feature of that object. Okay, there's a lot of terminology in relational databases. The relational model is based on formal mathematical concepts, and so it uses mathematical terminology in a very precise way. So we see the words like relation, instance, tuple, attribute, and things of that nature. Databases are more loosely based on the formal model, and so we tend to use more informal terminology like table, row, column, header, and that sort of thing. Okay, there is of course a correspondence between the formal terms and the informal terms, but when you read something about databases, including when you read my lecture notes, you may find that the author just flips between those two, between the two languages without really alerting the reader to the fact that this is going to happen. In particular, just as an example, a relation and a table are just two words for the same thing. So that Excel table that I just showed you is a relation, and it's also a table. Okay, so let's look at these words and describe the relevant features of those words. So a table then represents a collection of objects. This is sort of a slight simplification. We'll see later that tables are used to represent other things as well. But to begin with, a table represents a collection of objects. Sometimes they're called entities. That just means thing, basically. The Excel table represents a collection of movies. So the objects are movies. So what do we know? What features does a table have? Well, a table has a name, allowing the designer and user to refer to it. So you have to give the entire table a name. The one that we've just done, the table that I just showed you in the Excel spreadsheet, I'm just going to call that movie. Okay, not movies. It's just traditional that when you're talking about things, that the table is named with the singular noun representing the things that are being stored. The table has a header, so that's a row at the very top of the table that gives a name to each of the columns. And then a table has 0 or more rows, with each row representing one object in that collection. So a table can be empty. You can create a table and define and name the columns, but have no data in it. But usually, of course, a table will contain multiple rows, each row representing one thing. So earlier we saw the table movie, and here is another table which I've called book. Now, to make things as easy as possible and as intuitive as possible, I'm going to try to stick to the convention that I use this green fixed width font, so for table names. So, because it's easy to get confused between the names of tables, the names of columns, and so on and so forth. But if I can stick to this convention, then whenever you see something that's in typewriter font and in green, and in particular, if it's the singular noun for some class of objects, then you'll know that it's meant to be a table. Here's my book table. I've stored 3 columns, so there's 3 bits of information about each book that are being stored. Just the author and the title and the date of publication. Okay, maybe this is my list of classic books that I want to read by the end of the year. So in movie, each row represented an individual movie, and in book, each row represents an individual book. So I've highlighted one row there, and that refers to the book whose title is Cannery Row, which was written by John Steinbeck and first published in 1945. So this table is storing the information about 5 books. Just some more about the language. In the formal mathematical language, a row is sometimes called a tuple, and that notation, that terminology comes from mathematics, because in mathematics, a k-tuple, so a k-tuple is a mathematical object that stores k values in some particular order. So in particular, a 3-tuple stores a triple of values. And here's an example of a 3-tuple. We've got the first coordinate stores the value Steinbeck, and then the second coordinate stores Cannery Row, and the third coordinate stores 1945. So a row is also called a tuple sometimes. The order of the 3 entries in that triple or 3-tuple is obviously important. If I wrote down the tuple Cannery Row, comma, Steinbeck, comma, 1945, then that's still a tuple, but it doesn't make any sense in our application. It doesn't make any sense as a book. Okay, the columns. So the columns store or reflect the attributes of the class of objects. So an attribute is the name for some general property of an entity class. So an entity class then is the real world collection of all of those entities. So all the objects of the same class, of the same type. And an attribute is some common property that they all have. Each individual object has a particular value for each attribute, and that's what we store in the rows of the table. So in this example, in the book example, the attributes are author. Every book has an author, so that's a general property of the class of all books, and it's the value of that attribute for a particular object that is stored in the table. Every book has a title, so that's another attribute of a book, and a date of publication. And so we're storing 3 attributes. So we're storing when I designed that database, which didn't take much designing, then I just decided that those were the relevant attributes of the book, and so those were the ones that I was going to store in that particular table. Of course, the database designer decides what attributes to store based on the application. What would be an attribute of a book that I have not chosen to store in that table? Well, when a book is first published, it maybe has a particular number of pages. So number of pages is an attribute of the book class, but I've chosen not to store that because for my purposes, it is not relevant. So a database designer, first, before they do anything else, has to decide what attributes are we going to store, what is the relevant attributes, and which attributes are present in the physical objects, but we're not interested in storing their values. Okay, so a column then represents one attribute and the values of that attribute for all of the entities, all of the rows. So here I've highlighted the 3rd column. The attribute is date, that's the date of publication. Each book has its own different date of publication, and so each book has a particular value for that attribute. Okay, you may find that this is just all way too obvious for me to be spending so much time on, but what I'm trying to do is acclimatize you to the use of the terminology, because later we're going to need to use that terminology and not sort of have to pause and wonder what it means. Okay, suppose you were building a student database for a university. Then these are all things that are attributes of a student. I mean, every student has a name, and so probably you would want to save the name, so that would be an attribute that we would use. Every student has a height. You just measure somebody and they're a certain height. But do we want to store that in the university database? Is that a relevant attribute for the things that a university is doing, like storing marks and that sort of thing? Not really. Height is not really a useful attribute for a university database, so probably we would not store that. We would not bother with it. On the other hand, if you were creating a database for the fire department, then the height of firemen is important, and so maybe you would store that. Okay, eye color, well, we don't really need to store that. Nickname, so many people go by a nickname more than their own, given name. Is that relevant or not? Well, maybe it is in some contexts, because for a lecturer, it's nice to know what a student's preferred name is, so they can just call them by that. So that's a maybe, but probably not. So I'll put a cross through and a question mark. Address, well, we certainly need to know the student's address because we need to be able to send marks and so on. This is sort of becoming less important because more and more email address is becoming the critical thing. Date of birth, yes, we always store that. Favorite movie, not really relevant to their progress as a student. Student number, well, that's definitely needed, and that has to be a unique identifier. There can only be one student with each student number. So that's actually a special kind of attribute. That's an attribute where you can't have a repeat. So this has got a very special name. It's called a key attribute. Again, the database designer will have to choose which attribute is to be the key attribute or not. Gender, we do store it, not clear why. Weight, we don't store weight. Emergency contact, yes, everyone in the university database does have an emergency contact. Citizenship and visa status, well, we do need those because different rules apply to the university depending on a student's citizenship and visa status. So the database designer will consider the entire class of real life objects, the entire collection of students, if you like, and will then think of the properties that are relevant to the application being built. Okay, so we've got the rows, which are the things. We've got the columns, which are the attributes. The entire thing is just called a table or sometimes a relation. The word relation has a technical mathematical meaning here, and that's why we use that word. We don't need to know that for our purposes. We don't need to understand that for our purposes. So whenever you see the word relation, you can usually replace it with table for the time being. The number of columns of a table is called the arity of the table. So the book table has arity 3 and movie has arity 5. And finally, 2 rows of a table are equal if they have the same value in every one of the columns. So for example, 2 different books can have the same publication date, but if you have 2 rows where all 3 values are the same, then they really refer to the same book. And then you have to ask, why am I storing 2 rows referring to the same book? But we will come back to that consideration later. Okay, one thing that the table tells you is it specifies what bits of information are being stored and in what order. So the entries of the book table then must be ordered triples, and the first one must be the name of an author, the second one must be the name of the book, and the third one must be a date. Okay, so Dickens, David Copperfield, 1850 is a legal tuple. It's got an author in the first place, a book name in the second place, and a date in the third place. Well, a computer can't tell whether a particular string of characters is an author or not. So the only thing the computer can do at this stage is to insist that the first field is a string of characters. The second field is a string of characters. And the third field is a number. Okay. If you have a triple that doesn't have that form, then it's definitely not a legal triple in the book table. Okay, so some tuples are obviously incompatible, fundamentally incompatible with the table structure. So Dickens 1850 David Copperfield is can't be a valid row because the types are wrong. The third field should be a number and it's a string instead. So that's definitely an incorrect tuple. This second one is can't be a legal tuple of the book table because it's got the wrong arity. It's only got 2 fields, and we have to have 3 fields. On the other hand, this is a valid or a legal tuple, but it's not actually true. It's not a correct tuple in the table. One of the main features of databases is to preserve what's called data integrity. Basically, the database should make sure at all times, to the greatest degree possible, that the data that is in the table is actually valid data. Okay. Now, Excel will not stop me from entering the thing with the wrong types. Okay, I can just type those things in and it will just accept it. And then, so then we've got a table that has something that's obviously incorrect. On the other hand, a database, a proper database, will pick up that that doesn't have the right structure to be in the table and will throw an error. So one of the main roles of a database then is to catch data errors as soon as possible, prevent data errors. So a database can pick up this first error, can pick up this second error because they're just the wrong type of thing. A database without additional information can't pick up that third type of error. If somebody types something in that's just incorrect but has the right form, well, then there's nothing we can do. We'll see later how much more stringent data integrity rules can be enforced. Okay, in practice, when each column or attribute is defined, when the table is first created, the database designer must also specify what type of information is to be stored there, and that's normally done by actually specifying the computer storage type. Okay, for example, computers know when things are meant to represent numbers and know when things are meant to represent strings of characters. And so when the book table is defined, we would say, expect the first argument in any tuples that are going to be created, expect the first argument to be a string of characters, the second argument to be a string of characters, and the third argument to be a number. Okay, SQLite treats computer storage types in an, I'll just say types, treats types in a non-standard way. Okay, so what that means is that the SQL defines a very large number of types and allows users to have very fine-grained control over what type is going to be used for any field. SQLite does it differently. Okay, using SQLite is going to be slightly different to using other vendors' SQL implementations, and so where it's relevant, I'm going to try and point out to you where SQLite is different from the standard and where it adheres to the standard. Okay, so sorry that was a little bit long and slow, but once you get all of that terminology very clear in your head, it'll really help us later in the semester. Okay, see you in the next video.